Okay, the next thing we're going to look at is something that's called the Copernican Revolution. And that's named after a guy named Nicholas Copernicus, who, as we'll see in a little bit, was very important for the evolution of our knowledge in how our universe works. Okay, we're going to look at what's called ancient astronomy. We're going to go back in time to the earliest people and what they knew about the things that existed in the night sky. Astronomy is sometimes called the oldest of the sciences because when early humans looked up in the sky, they really asked the big questions. What are those points of light? Why do they move the way they move? What do they do? How do they affect our world? And understanding the motions of the planets and the stars, and that led to things like being able to predict growing seasons and other things that were very important for improving their lives. And so really astronomy was the first science that was actually applied in a way to make people's lives better. Now, ancient civilizations all observed the skies, and many of them would build structures to mark astronomical events. We've talked about things like the summer solstice and the winter solstice. There are structures that were built in the world that would mark these events almost like a calendar. And, maybe the most famous of these is the famous Stonehenge monument in Great Britain. And you can see here in this inset image that on the sunrise at the summer solstice, that the sun comes up from the horizon and shines right between these two columns. And so on the day where the sun comes up perfectly between these two columns here, you know that the days after that are going to start getting shorter. And so that's what I mean in the sense that it could be a calendar. It lets you know when the seasons are going to be changing. It's a marker for the passage of time. And we really take for granted, things like having a calendar with so many days in a month and, adding in leap years to make the calendar be corrected. These things, we know about them today. We take them for granted today. But to the people that lived thousands of years ago, it was a great mystery why the world was the way the world was, and it took a long time to figure these things out. Here's another famous ancient structure. This is the Bighorn medicine wheel, which was this structure where the spokes of this wheel are aligned with the rising and the setting of the sun and other stars. So again, this is something that could mark the motion of the stars and the planets in a systematic way. Ancient people were actually really clever in how they studied the stars and the planets and the moon and how all these things move. And really, it's really impressive what they were able to discover just using their brains and their naked eyes. Here is another structure. This is a temple in Caracol, Mexico. I probably mispronounced that. If so, I apologize. But it has many windows that are aligned with different astronomical events. So when certain things shine through certain windows on certain days, that marks parts of the year. So this slide shows a list of some of the things that ancient astronomers were able to observe with their naked eye. The sun and the moon, of course, and the stars. They were also able to see 5 of our solar system's planets. They were able to see Mercury, Venus, Mars, Jupiter, and Saturn. Uranus and Neptune cannot be seen by the naked eye. In order to see those, you have to have a telescope. But just with their eyes, they could see these planets. Now, one of the things that's really interesting is that if you just look up at the night sky and you see a planet, it looks very similar to a star. And so you might ask yourself, how did the ancient people, if they didn't have telescopes, how did they know that they were looking at a planet and not a star? And there was something very, very different about planets compared to stars. Now, we talked about constellations. For example, we talked about the constellation of Orion. And so here I've sketched in some spots. Here's Orion's belt. Here are the other stars that make up Orion. The reason that Orion can be a constellation is all these stars move together in the night sky. In other words, if you go out tonight and you find Orion and you keep looking at it, the position of the entire constellation Orion will change as the hours tick by. And if you go out the next night and you look for Orion, you'll find the constellation of Orion, but it'll be in a completely different part of the sky. It will have moved. But the thing is, all the stars move together. They keep this pattern because the distance between each star doesn't change relative to one another. But a planet is something that is very, very different. So if you're looking at Mars, and Mars is right here in the night sky, what you're going to see is that Mars will move against the background of the stars. And so the position of Mars relative to this star, for example, will change from hour to hour and night to night. And so all the stars seem to move together and they keep their pattern. The planets, they move independent of the motion of the stars. In fact, the word planet comes from the Greek word for wanderer, because it seems to wander around the night sky, whereas the stars all move together. Now, there's also another difference, and it has to do with how we perceive them. And it's the fact that stars twinkle and planets don't. Now, it might be hard for you to understand what that means if you live in a big city, because if there's a lot of light pollution, the stars look very dim and they don't seem to twinkle very much. But if you go out into the country where there's not a lot of light pollution, you'll actually see that the stars, they kind of wink and twinkle at you as you're going. And that has to do with the way that the light passes through the atmosphere. And I'll explain that a little bit more detail in the lecture. It's kind of hard to do in this video, but just be aware of the fact that there's two differences between the planets and the stars. One is that the planets move independently, whereas the stars all move together. And then the other is that stars twinkle, but planets don't. And you can remember which is which because there's a whole song, Twinkle, Twinkle, Little Star. I apologize for singing, but you know what I mean. There's a song that will remind you which ones twinkle and which ones don't. So, stars twinkle, planets don't. So here is a summary of some more differences of planets with stars. So we've already talked about a couple of these. So the movement of the planets move with respect to fixed stars. Now, also the planets, they get brighter and dimmer. They don't twinkle, but over time, over days and weeks and months, they change how bright they are. And that's because they're getting farther away and closer to us, where the stars are basically, they're not getting any further away or closer to us. I mean, they might be a little bit, but compared to how far away they already are, the change is, negligible. Another thing that's interesting about planets is that they change their speed. When you're looking at them in the night sky, they speed up and they slow down. Whereas the stars all seem to move together kind of at the same rate. That's because we perceive the motion of the stars because we're on a planet that's rotating around its axis. And so we're underneath the stars, rotating out from underneath them, but we're looking up at them so it looks like they're moving around us overhead. But the planets, they kind of move across the field of stars and they speed up and they slow down. They actually change speed. And that is a unique thing to planets compared to the stars. And then finally, the planets undergo something called retrograde motion. Now, if you know the word retro means backwards. You might have heard of retro rockets, which is to backward firing rocket to slow your descent. You might have heard of retro fashion, which would be like fashion from the 1970s. You're kind of looking back at time at earlier fashions. Well, retrograde motion basically means a backwards kind of a motion. And you can see this in this weird picture over to the right. Up above, you can see lines that are showing motions of some of the different planets. And down below, you can see sort of one of the paths. Now, this is a path of a planet. Let's say this might be Mars, for example. And so if you're on the Earth looking up at the night sky and you watch Mars from night to night, the motion of Mars will change where it is in the sky. It'll move across the sky. But eventually what happens is it turns around and it goes in a backwards direction. it actually goes backwards for a while, and then it turns around again and goes forwards again. It makes these kind of loop-de-loops, and that's kind of weird when you think about it. And this was something that ancient astronomers observed, and they saw these loop-de-loops, the motions of the planets, and they thought, man, that's some crazy stuff, and it was very hard for them to explain. Now, this picture is a very famous picture of one of the earliest models of our solar system. This was a model developed by a guy named Ptolemy. Ptolemy, his name is spelled in kind of a weird way, but that's his name, Ptolemy. And he came up with this model for the solar system, and this is what ancient people believed. They believed that the Earth was special. They believed that the Earth was the center of the universe, and everything in the universe moved around the Earth. And this was actually an idea developed by ancient Greek philosophers, and then years later, the Catholic Church felt like this was a model that fit best into their worldview, and they actually made this part of church doctrine, that the Earth was the center of the universe, that God had created the Earth as being this kind of special place. And the Ptolemaic model that was created by Ptolemy, that's what we call it, the Ptolemaic model of the solar system, it had everything circling around the Earth, and so you can see the moon is circling around the Earth, Venus is circling around the Earth, the sun is circling around the Earth. And if you imagine the Earth is sitting still, that the Earth is not moving, this model kind of makes sense. It's not right, but it makes sense. And actually, more than makes sense, it's actually in a lot of ways a really good model because it can make predictions that are true. It can tell you where the planets are going to be at certain times of the year in the night sky. And so this model actually fits data. It makes a good model. It just happens to be wrong. It's a really complicated model because remember I told you when you're looking at the motion of the planets, they make these kind of loop-de-loops. So here's the idea of Jupiter. Jupiter's not only going around the Earth, it's also forming these kind of loop-de-loops as you go. And so that's a weird kind of motion. It's a very, very complicated motion. Now, of course, even though this model in some ways is a good model, it fits data, it can make predictions that are accurate, it also just doesn't correspond to reality. We now know that the Earth is not the center of the universe. Remember, we even talked about that. We talked about something called the Copernican principle that said the Earth is not the center of the universe. The Earth does not occupy a special place in the universe. And so this comes from the realization that while this model works, it's really inelegant. It's really kind of crazy and complicated. And many, many years ago, a guy named Nicholas Copernicus, he wondered, is there a simpler way to describe what we see in the universe, in our solar system? And he came up with a different model that explained the motion of the Earth, the motion of the planets, and it was a much more simple and elegant model. And it also was much, much closer to being the correct model. We now know we've sent satellites and probes out into space. We know how the universe behaves. But back then, it was very controversial. In fact, Nicholas Copernicus was so nervous about publishing his discoveries, he waited until after he died before he had them published. It's called publishing posthumously. And he did that because he was afraid that he would get in trouble with the church. The church had already said that this picture, this is the way that the world is. It's not in the Bible or anything like that. It's just the Catholic Church decided that this was the way the universe was. And back then, the Catholic Church was the only church in the Christian religion. And if you went against them, they would excommunicate you. They would kick you out of the church. And if you got kicked out of the church, it was believed that you could not go to heaven. And so that was a very severe punishment to be kicked out of the church because it would mean you couldn't go to heaven. And that was something that the church would hold over people and scare them with. And so Copernicus didn't want to go against the church, so he published his work posthumously after he died. And people read it and they recognized that his model was much simpler and much more elegant. And later on, we'll see that evidence accumulated that showed his model was actually much more correct than Ptolemy's model. So what are the big two differences now? Let's recap. Now, Ptolemy's model was what's called a geocentric model. And in fact, we can note that the title of this slide is the geocentric universe. Now, you might remember the word geo is the root word for words like geology and geography. The word geo basically means the earth. And so when you talk about a geocentric model or a geocentric universe, this is a model that of the universe where the earth is the center. So this picture that we see in this slide, this is a geocentric model. Geo meaning earth and centric meaning center, and so the earth is the center. Now, the model of Copernicus was what was actually called a heliocentric model. And the heliocentric model is a model where the sun is the center. And so helio is a word meaning sun. And so heliocentric means that the sun is the center. And so Copernicus's idea was twofold. His first idea was the idea that the solar system was heliocentric, that the sun would be the center of it. And so you can imagine the sun. And then he had the idea that the planets would go around the sun. And so instead of everything going around the earth, his idea was that everything went around the sun, with one exception. The earth would go around the sun, but the moon would go around the earth. He recognized that the moon would go around the earth, but all the planets would go around the sun and not around the earth. And this was the idea that the sun was the center of the solar system, a heliocentric idea. Now, the other aspect of his model was the idea that the earth would be spinning on its own axis. And so by spinning around the axis, the sun would create day and night because the sun would only be shining on one side of the earth at a time. And as the earth spun around its axis, the side of the earth that was presented to the sun would change, and it would come back full circle every 24 hours. And so the two ideas were that the earth was going around the sun and the earth was spinning on its own axis. And these two ideas together make a much simpler motion than the crazy loop-de-loops of the geocentric model of Ptolemy. And not only was it a much simpler model, it could also explain everything that was observed. Now, you guys might remember we talked about Occam's razor. Occam's razor was the idea that in science, if you have two different models that describe some phenomenon in nature, that the simpler model tends to be the correct model. And so Copernicus realized that his model was much simpler, and he thought that it was much more likely to be a correct model. And so he arranged for it to be published after his death. And he didn't get it exactly right. He, for example, said he thought that the planets would move around the sun in circular orbits, that the paths would be circles. It turns out that's close, but not quite exactly right, and we'll talk about that later. But overall, his model was startlingly good, and it really opened up our understanding of the universe. So let's look at how it can explain this idea of retrograde motion. So we might have here the sun. The sun is in the center. And then we might have the Earth, say, here. And the Earth is going around the sun. And then we might have Mars. Mars is out here somewhere. And Mars is also going around the sun. And so the thing that you have to recognize is that the Earth is going faster than Mars. And so the Earth is going to go around its orbit faster than Mars, and it's going to loop around. And so imagine that you're on the Earth and you're watching Mars. And so when the Earth is over here somewhere and it's looking at Mars, and then the next night it's over here somewhere, or a month later, whenever it is, Mars is getting closer and closer. But then the Earth is over here, and the Earth passes Mars. And Earth is going faster, so it'll leave Mars behind. And so at this point, Mars is getting further and further away. And so in that sense, you can kind of see that the way that Mars looks from the position of the Earth is going to change in weird ways. If you're outside the solar system looking down, like we're kind of looking down in this picture, it's clear the Earth goes in its loop, Mars goes in its loop. My picture's getting messy, but hopefully the idea is very simple. The solar system motions are really simple. But if you're standing on the Earth is going around the sun, the Earth is spinning on its axis and looking at Mars as Mars is going around the sun. That motion appears to be very complicated. But if you understand what it really is like, that shows you that it's actually much more simple. So continuing on with our model of the solar system being heliocentric, that means the sun is at the center. This slide looks really, really complicated, but what it's showing is how the planet Mars seems to make that weird loop-the-loop, that backwards retrograde motion that we were talking about. And so here we see the Earth, and there's basically 12 months in a year, so every month the Earth is at a different position, and during that same time, you can see that Mars is also in a different position. So this inner circle represents the orbit of the Earth, and this outer circle here represents the orbit of Mars. And so you can see when you start month 1, Mars is actually right here, but you're on the Earth looking at Mars, and you're looking at it against the backdrop of the stars, and so Mars actually appears to be over here somewhere. And so, as the Earth moves from there to there in month 2, Mars has moved actually from here to here. But the angle, this blue line, is showing the angle of Mars to the Earth. And so you're looking at Mars, and it actually appears to move to there. So it's in month 1, Mars looks like it's here. But over the course of the first month to month 2, Mars seems to move in the night sky to here. Month 3, the Earth has moved along its orbit to here, Mars has moved to there, and Mars has moved in its position. Now what gets really interesting is from month 5 to 6. So here's month 4, here's month 5, here's the Earth. Now what's happened is that the Earth is actually catching up to Mars in month 6, and then in month 7 it's moving away. And so you can see this idea in month 5, here is where Mars is, but because here the Earth is on the right side of Mars, and over here the Earth is moved to be on the left side of Mars, and so you can see the angle radically changes, and the apparent motion of Mars is to go back on itself. So if you look at these pictures and look at month 1, month 2, all the way up to month 11, you can see where Mars is going to appear to be in the night sky, and if you track that motion, you see it seems to be moving in a straight line more or less, and then it does this crazy loop-to-loop, and then it goes back to being in a straight line. And this cycle repeats over and over and over again as Mars and Earth complete their respective orbits over and over again. So here is sort of a summary of the ideas that were put forth by Copernicus. The first idea is that the Earth is not the center of everything. We talked about this previously. This is the so-called Copernican principle. This is part of the Copernican revolution. The center of the Earth is the center of the moon's orbit. So the moon is actually orbiting the Earth. But the planets, all the planets revolve around the sun. And so the planets move around the sun. The stars are very much further away than the sun. And the apparent movement of the stars around the Earth is due to the fact that the Earth is rotating on its own axis. So that apparent movement is due to the Earth's rotation. And please stop screaming. Similarly, the apparent movement of the sun around the Earth is due to the Earth's rotation as well. And then finally, the retrograde motion of the planets is due to the Earth's motion around the sun. And that leads us to the birth of modern astronomy. And the thing that separates modern astronomy from ancient astronomy is the invention of the telescope. The telescope really is what made astronomy just explode as a science. I mean, the knowledge about our universe just became so much more vast once the telescope was invented. And it was invented around 1600. Now, Galileo learned about the telescope. He's a very famous scientist. You've probably heard of Galileo before. and he built his own telescope, and he used it to make observations. And over on the right, we'll see this is actually a picture of one of Galileo's actual notebooks. And we'll talk about what that picture says in a minute. But he made many discoveries. One of the things that he discovered was that the moon has mountains and valleys. He was able to look at the moon through his telescope and see structure that reminded him of structure that is visible on the Earth. We have mountains and valleys on the Earth as well. People didn't know what the moon was before. It was just some big glowing ball. But once Galileo was able to look at it through his telescope, he could see features that were very Earth-like in a lot of ways. And so he recognized that the moon was just another physical body like the Earth. It's almost like a mini planet circling the Earth, just as the Earth circles around the sun. He also used his telescope to see sunspots. Now, let me caution you, there are very special things you have to do in order to look at the sun through a telescope. Even looking at the sun with your naked eye is very dangerous. You can harm your eyes. You can damage the retinas of your eyes if you try to look at the sun. And if you try to look at the sun through a telescope, you will put your eyes in much more danger of getting injured. So you do not want to look at the sun through a telescope ever unless you know what you're doing. Now, Galileo had a system where he was able to project the sun onto a wall. We have actually in our lab a telescope with a solar filter that will let us look at the sun later in the semester. But one of the things that he noted was that the sun had these spots on it that are called sunspots. And he also recognized, he would see if this is the sun, he would watch the spots and he would see the spots move to the right and then they'd vanish. And then they, a day or two later, they'd come back the other side. And he would see these sunspots basically moving around the sun, and he recognized that the sun itself had to be rotating. And so that was a discovery that Galileo made. He made a discovery about the rotation of the sun. But these last two discoveries that Galileo made were the most important probably in terms of his contributions to astronomy. The first of these two big things that he discovered was the idea that Jupiter has moons. And this is actually what this picture on the right is showing. So the circle here represents the planet Jupiter, which he was able to see through his telescope. And then he saw these little bright points of light. And when he would look at it on a different night, he would see that the points of light had changed. So here the points of light are on this side, here they're all on that side, here they're all on the other side again, and he could see, and one of the things that you could see is sometimes he could only see 2 points of light, sometimes he could see 3, sometimes he could even see 4. Here's 4 with 1 on the left and 3 on the right. He was observing these things, and what he recognized was that the planet Jupiter, these little tiny points of light, were moons. And they were going around Jupiter. They were orbiting Jupiter. And so sometimes the moons would be behind Jupiter, so he couldn't see them. Jupiter was in the way, blocking them. So here, for example, you can see that there was only 2 moons, and so the other 2 were behind Jupiter. Here you can see there are 3 moons that are visible, so one of them is behind Jupiter. Here you can see all 4 moons are visible. Now, this was a huge, huge discovery, the fact that Jupiter had its own moons. Because remember, in Galileo's day, the main idea was the idea of the geocentric universe, the idea that the Earth was special and the Earth was the center of everything in the universe. Everything had to go around the Earth. This was actually the doctrine that was supported by the Catholic Church. And Galileo now had proof that there were things that didn't revolve around the Earth. Here's something that's revolving around Jupiter, that Jupiter itself has moons. So that was a major dent in the Ptolemaic geocentric model of the universe, that the Earth was a center. But then Galileo also observed through his telescope the planet Venus, and he was able to show through the telescope he could see that Venus had phases. Now, that may be, at first statement, it may not seem to be that special, but it turns out it's really special. When you look at the phases of Venus, they behave in a way that cannot be explained if Venus is moving around the Earth. They don't behave in the same way that the moon has phases. And so they can only be explained if Venus and the Earth are both moving around the sun based on the motion of those two planets around the sun at different points in the year. And so the observation that Venus had phases that behaved in the way that the phases of Venus behave was proof that the geocentric model of the universe was wrong. And it supported the idea that the sun was the center of the solar system. In other words, Galileo basically proved that Copernicus's model was correct. And that was a huge change in our understanding of the universe. And it was, at the time, a really, really big deal.